ready. So please go ahead.
Okay. Yeah, thank you. Hello, everyone. My name is Andreas Kunz. I'm a senior researcher at Lenovo, and I represent Lenovo in 3GPP meetings, especially for the Security Architecture Group, SA3. This talk is about 5G security, especially about the basics of the 5G security, the phase 1 of 5G, because all the other features in phase 2 and in release 17 will be basically built on the phase 1. I will give you a short outline of the talk. So we have the introduction about the 5G security overview, basically. We have some background on the 4G weaknesses. We have the 5G security domains, some of the new features in 5G security, the new architecture. This is also novel in 5G. We have the security associations, and we have the new feature of the subscription identifier privacy and the new key hierarchy. I will go into the most important 5G security procedures. I will give you a short overview of the procedures and how they relate to each other. So we will start with the authentication and the primary authentication with the two different procedures and methods specified. I will introduce to you the Nas Security and with the new features of the initial NAS message protection and the multiple NAS connections. And then we will go to the access stratum security with the access stratum security mode command and the new user plane security enhancements. I will also introduce to you briefly the key derivation due to handover between different GNODBs or due to RSC connection reestablishments. Then I will show you the new feature of steering off roaming as well the UE parameters update. They are in principle the same procedure. Then the new feature of the secondary authentication with the data network. And then the EPC interworking with the security context mapping and the non-standalone security. We will have then the service-based architecture security. This is very new because of the new concept of this architecture. We have the interconnect security, which is also following the principles of the service-based architecture. And then we have the new non-3GPP access, which is also a new authentication procedure, which is able now to carry the same authentication methods as for primary authentication in 3GPP. Then, last but not least, we have the visibility and configurability of security features. I will give you a very, very brief outline of the standardized release 16 features, which is 5G phase 2, and an outlook on release 17. All these features are specific to the security group. There are different features in each group in 3GPP, but not all are related to security, and not all groups are on the same speed on standardization. So the security group is always a little bit behind. There's already groups working on requirements for release 18. Let's go with the introduction. And I will give you an overview about what were some issues in 4G. We had some potential threats in 4G, like you may know, you could have a so-called IMSI catcher. The IMSI was sent in clear in the initial attach message. We had the issue that due to some implementations, the temporary identity TIMSI was not changed. There was a so-called WhatsApp attack. You could type or store the telephone number of your victim in your phone and just type and observe the paging messages of the GNODB, and the temporary identity won't be refreshed. So you could basically track your victim. There was no user plane integrity protection. This is a threat which was discovered by the Alta attack, where you could do some DNS hijacking. And without knowledge of the UE and the network, you could redirect the user to a potentially malicious website. There is the bit down possible to GSM, and GSM security is much weaker than in LTE and easier to break. There were different threats due to the SS7 and diameter protocols for the interconnect. There were threats where you could only know the telephone number of your victim, and if you had access to the SS7 network, you could start anytime interrogation messages to the HSS to retrieve the last known cell ID where the user was residing. So these were some issues in 4G, and of course in 5G, the idea was to cover them as best as possible. 5G basically looks very similar to 4G with respect to the security domains. We have an application security domain between the user and the service provider. We have the access security domain between the UI and the home network and the serving network and the access network, which is established during primary authentication and where you derive the keys for the different security protocols. And then we have the user domain security between the mobile equipment and the SIM card. The mobile equipment and the SIM card comprise basically the user equipment or UI, which is the phone. Then we have something very new. This is the service-based architecture security domain, which is between network functions and also between mobile networks. And then we have the network domain security. This one is between network elements, like between a G node B and then access mobility function, AMF. So you can have some IPsec tunnel where you have the traffic of all users inside to protect them. Then what is not shown in this figure is the visibility and configurability of security. This basically means there is the possibility that you could display on the phone whether a specific security feature is turned on or turned off. But practically this feature was already there since UMTS with a simple on-off. Now the granularity is much finer, but it was not really implemented so far. Let me give you some very brief overview. Also, most of those features will be discussed later in this talk. So we have the increased home control, which is part of the authentication procedure. We have the RAN security split between control unit and our central unit and the data unit, which is a very RAN specific thing. Then we have the 5G and 4G interworking security. We have two new authentication methods in 5G. We have the enhanced subscriber privacy, which is an important feature, and is trying to tackle the IMSI catcher. We have the service-based architecture, and we have the non-standalone security, as well as the visibility and the configurability. Now it is possible to have two NAS connections. It's called multiple NAS connections. We have user plane security enhancements, which is also very important to enable the user plane integrity protection. We have the PLMN interconnection security based on the SPA security, and we have the secondary authentication with the data network. This is the 5G security architecture. There are a few nodes or functions inside which are mostly not shown in other architecture figures, like if you look at the network architecture from the system architecture group. We have, for example, the SIDF, the subscription identifier deconcealing function, which is residing in the UDM. When the UI sends an initial registration request, it sends its concealed identity, and the SIDF is able to deconceal it to the real identity, the secret identity of the UI. Then there is the ARPF, which is the repository function for the authentication vectors, when the thief, the security anchor function, decides to authenticate the UE, then it will query, or the AUSF will query the ARPF for an authentication vector. And the AUSF is the authentication server. Authentication takes place always between the UE and the AUSF for primary authentication. There are also other authentications, like the secondary authentication. This is between the UE and the data network. There's a new authentication, like the slice authentication. This is also with some vertical service provider. And with the authentication result, the UE would then get access to establish a PDU session, or in case of slice authentication in Release 16, to access a specific network slice. There's also some other new functionality, which is the N3IWF. This is the terminating point for untrusted non-3GPP access for the IPsec connection between the UE and the N3IWF. There are different 5G security associations. They are built up with the different protocols and established with different commands, which we look at them at a later stage. So the first one would be definitely the primary authentication, which is performed between the UE and the AUSF, and the AUSF fetches the credentials from the UDM, the subscription repository, where you have the SIDF and the ARPF inside. Then, after primary authentication, you would do a Nas Security setup, the so-called non-access stratum security mode command and complete, which is establishing the Nas confidentiality and integrity of this protocol. After this is performed between you and AMF, the AMF would provide the key to the RAN, and then the UE could set up the RC confidentiality and integrity. This is the so-called access stratum security mode command. And if there is a security policy, the UE would also set up the user plane confidentiality and integrity. There is this new authentication method, which is shown here in black with the UE via the SMF and the data network. This is an EAP-based authentication, and it is relayed basically by the SMF, and the SMF sends this to the UPF, then to the data network. Only after this authentication is performed, the UE can establish a PDU session and then has IP access to this data network. This is one of the most important features. This is the subscription identifier privacy. As said before, in 4G, in the previous generations, the IMSI was transferred in clear text over the radio interface at the initial attach message. Only this message, but this was enough to build these IMSI caches and try to fetch the IMSI of your target UE. In 5G, the idea was to prevent this, and the user should conceal the identifier in a so-called SUKI, subscription concealed identifier. So only this is basically based with a public and private key pair. The public key pair key is stored on the user. The private key for deconcealing is residing in the SIDF in the UDM. There are a couple of parameters in order to do this. So we need to have the home network public key basically in the user. We need a public key identifier because you could have more than one public key. You would have to have the scheme profile, and you have to have the protection scheme identifier, because we have specified two different profiles for elliptic curve integrated encryption scheme, and whether you use the other or the one or the other, there are different key lengths, there are different, slightly different parameters. And the main thing is that the home network key has to be stored in the user. And then whenever the UI makes some initial registration, it will send the subscription concealed identifier, the SUKI. In all following up re-registrations, the UI gets assigned a temporary identifier, a so-called 5G GUTI, a globally unique temporary identifier of this UI, and then this is then used for all the following re-registrations for mobility or for pageability. There are two different protection schemes at the moment, and we have the null scheme, which means there's no protection. So the SUPI would be basically equal to the SUKI, which is not preferred. And then we have the elliptic curve scheme. The SUPI itself can now have two different formats. Before, in 4G and before, we always had this IMSI format, which had the mobile country code and the mobile network code for routing. And then you had the mobile station identity number. So, and this telephone number basically is now concealed with the public key, and then appended with the parameters to the MCC MNC. This would be the IMSI type of the SUKI. There's also a NI type where you can have a username at realm, and then the username part is encrypted and appended with all the parameters to the realm to form the SUKI. There are basically a couple of issues where you could still get the SUPI even you want to have the SUPI encrypted all the time. And one would be that the UI doesn't have a user which is capable to store the home network public key and the other parameters. Another one would be the home network operator did not provide a public key, or the third option would be that the home network provider wants to use the null scheme. And then you don't have apparently no protection of your permanent identity. But the mechanisms are in place. So this is the key hierarchy. This gives you a little overview on how the keys depend on themselves. We have a root key K, we have the CK-IK keys, and those are used in case of 5G AKA. If you want to use EAP AKA prime, the other authentication method, you have to derive the intermediate keys CK prime and IK prime. And then for the authentication, you use the KAUSF. And then what is important is the AUSF will derive the KSIEF. In the key derivation, the serving network name is included because the KSIEF is residing in a serving network name. So only this serving network can use this specific KSIEF, and you cannot basically fake the location of the UI. Then, what is also something very new, including the serving network name in the key is not new, because that was also happening with the MME key, KASMA, which is given to the MME. But here, what is new is the derivation of the KAMF. The SIEF and the AMF are basically co-located. There was the idea before in the study phase of 5G that the security anchor function could serve different AMFs, but so far one SIEF is co-located with one AMF. So, but now the SIEF will generate an AMF and includes the private identity, the secret identity SUPI in the key derivation function, as well as the ABA parameter. The ABA parameter basically is for anti-bidding down and indicates the security features of the network. So far, there's only one security feature possible, which is the 5G phase 1 indication. But this should prevent that you get bit down to any other earlier generation of the mobile network. Then from the AMF, you directly derive the N3IWF key in a similar way as the G-Node B key. So this is also a new key here. And then what is very new is the user plane integrity protection key, the UP-int key shown below, to protect the traffic between the UE and the G-Node B. Basically, the algorithms for key derivation and the key lengths are exactly the same as in 4G. So we have 128-bit keys on the radio level. There are at the moment studies going on to extend those key lengths to 256 bits, but there are different requirements on performance and backward compatibility. So let's go to the 5G security procedures. This is an overview of the security procedures. You see in step 1 the initial NAS message, and in step 8 the initial NAS message response. Basically, in this case here, the initial NAS message would be the initial registration request. So all these procedures are executed in between before the network acknowledges that the registration was successful. There's something like the UE parameters update. This could be, for example, also executed within the registration request, but it was foreseen before that it should be outside the registration request. So the first procedure basically is the primary authentication. You need to authenticate with the network that it can access the network. Then there's some very new feature, that's the home control link to subsequent procedures, that the UDM knows that the UE is successfully authenticated. Then we have the Nas Security mode command. If this is successful, the RAN performs the access stratum security mode command. Then you can enable the security policy with user plane integrity protection. You could do the steering of roaming, which means the home network operator can send a list of preferred PLMNs or access technologies, and then you acknowledge the registration procedure. After the registration, you could perform the secondary authentication and then the UE parameters update. We will go through now in exactly the same order of those procedures and see how they look like. The primary authentication is performed always between the UE and the AUSF. The UE and the sieve can reside in the serving network, but the AUSF and the UDM are always in the home network. The UDM is the one that selects the authentication method. We have two authentication methods, as said before, 5G aka and EAP aka prime. And so in the flow here, to trigger the authentication, it would be some initial registration method with a SUKI or a re-registration method with a 5G GUTI. Whatever it is, the sieve decides that authentication is required and sends an authentication request to the AUSF, and then asks for an authentication vector from the UDM. In the UDM, if SUKI is included, then the deconcealment will take place and to retrieve the SUKI. If the UE sent a 5G GUTI, then the sieve will already include the SUKI because the UE was registered before. This is the authentication procedure in case of 5G aka. This is basically based on the 4G procedure, EPS aka, but it has the enhanced home control, which was missing in 4G. So this procedure is specified in 33501. And one other difference to 4G is that you only provide one authentication vector to the AUSF for one authentication run. So it means if the UI needs to be authenticated, the AUSF always has to ask for another authentication vector to the ARPF. So as said in the previous flow, the UDM selected the authentication method, in this case 5G AKA. It will send the authentication vector to the AUSF. The AUSF will calculate the challenge and the expected responses and the hash of the expected response. So it will send the hash of the expected response with the challenge to the sieve. The sieve will send the challenge to the UI. The UI will calculate the response. The sieve will calculate the hash and compares it with the expected hash. If this is okay, it indicates this to the AUSF with the response of the UI, and the UI will, the AUSF will verify the response whether it matches. And if this is okay, then the AUSF will provide the SUPI and the K sieve to the sieve, so that the next procedures can take place. So this verification in the AUSF is a so-called home control. This means that the home network operator always checks whether the UI is really in this visited network or not. The same applies to EAP aka prime. This is an ITF specified authentication method, and EAP methods, there are many different EAP methods, and the good thing is they are also applicable to other procedures. So we had EAP methods before for the non-3GPP access in 4G, but they were not linked as closely to the or treated as similar as the 3GPP access. But now we have two authentication methods which are basically on the same level of support in the 5G core network. So here it's basically the same, just that the AUSF provides the challenge to the sieve and no expected hash response. So the UI will calculate the response, sends it back to the sieve. The sieve will just forward it, and the AUSF will do the verification of the response and whether it matches. So here we do have the same home control as in 5G AKA. We don't have this extra verification in the sieve. So the increased home control is some indication to the UDM basically, because the UDM should know whether the primary authentication, if it's 5G AKA or EAP AKA prime, was successful. So after the authentication, the AUSF will provide the authentication result to the UDM, and UDM stores the authentication status until the next re-authentication will take place. So now if the AMF would send a request to the UDM, then UDM can authorize this request based on the authentication status. This is also something very important because the AMF and sieve are in the serving network and may be a roaming network. Now we come to the Nas Security. One important feature is the initial Nas message protection. The initial Nas message has the problem that the UI and the AMF don't have a common security context at this time, so it needs to be established. And this means that all parameters in this message are sent in clear text. This is a problem for some of the information elements. The idea now is that the UI sends the initial NAT message, and only with a very limited set of information elements which are needed by the AMF to trigger the authentication with the UI. After the authentication is successful, the AMF will send a Nas Security mode command, which we look in more detail in the next slide, and will set a flag and ask the UI to send the full initial NAS message with all the information elements in the response. Then, because the response, or with the NAS security mode command, the UE has enough information to derive the keys for the NAS message protection, and then can send the NAS security mode complete message ciphered and integrity protected. So let's look at the NAS security mode command, or NAS SMC as it's called. And the AMF has the KAMF and derives from it the NAS keys for integrity protection and ciphering. So we'll send the NAS security mode command, which is integrity protected already, and it has a couple of parameters like the UE security parameters, which are replayed and sent in, originally already in the initial NAS message. And then we have the selected NAS algorithms. You have the key set identifier so that the UE knows which KAMF to use. And then it can set a flag to request the complete initial NAS message. And there may be this anti-bidding down parameter, and it may be a flag to request the permanent equipment identifier. The permanent equipment identifier, PEI, which is basically the EMA before in previous generations, is now also not sent in clear text over the air interface anymore. It's always sent when the NAS security is set up. So the UE then calculates its NAS keys based on the KAMF, because it has now enough information and can send the complete NAS message or the security mode command or whatever was requested by the AMF in the response, in the security mode complete message. And then AMF and UE can start ciphering and use well, the UE already starts ciphering in step 2b, but the AMF will start ciphering once this security mode command complete message is received. There are now multiple NAS connections possible. This is because the non-3GPP access is treated now in the same way as the 3GPP access. So we can have primary authentication running over non-3GPP access, which could be a wireless LAN, and over the 3GPP access like 5G. And there are two possibilities. Even the non-3GPP access provider could act like a roaming network, and the UE would have then, in the specific case, two different AMFs. And if it would be connected to the 3GPP access and to the non-3GPP access. So it would be connected to two different PLMNs. So the UE would have to have two different security contexts. And then there's the other version that the UE, that the non-3GPP access belongs to the same operator. Then a common security context is used for both. But since the N3IWF key is on the same level as the G-Node B key, the uplink NAS count is used, and the access type distinguisher to derive those two keys, to make sure that you have two different keys on the two different links. Now we go to the access stratum, to the lower layers. So in order to establish the security on the radio interface, you need the so-called ASSMC, the access stratum security mode command message. This is the same like the G-Node B retrieves the key from the AMF, the G-Node B key, and can derive all the subsequent keys for RSC and user plane security. And then it sends the AS security mode command, which is similar to the NAS security mode command, integrity protected and not ciphered. The UE will also derive the same set of keys like the G-Node B. And then, because here it's the AS security mode command contains the security algorithms for RC and user plane. And then you can only you can have two different sets of algorithm, but independent how many PDU sessions you would have on the user plane, they would always use the same security algorithms. So the UI would then derive the same keys, and then will send the access security mode complete message to the G-Node B and start ciphering as well. The AS security mode complete message is only integrity protected in this case here. And after this procedure, you could set up the security policy. The security policy, we will look at it in the next slide. User plane security is something important. It's basically the integrity protection of the user plane. This was a big problem until 5G. Now the chipsets are so powerful that they can do this computation also for various bit rates. So in 4G, there was also user plane integrity protection, but it was only available for so-called relay nodes, and in practice, they were most likely never really implemented. And then we have this new feature now in 5G, and it is indicated to the G-Node B with a security policy on a PDU session level. So when the UI asks for a PDU session, then the SMF will query the policy control function for the security policy, and the security policy will then say what to apply for this specific PDU session. There are different policy levels. We have required, which means you have to use user plane integrity protection. If it is preferred, then the G-Node B can handle it based on capabilities or load situation. And then if it's not needed, then it will be always disabled. The problem is if the G-Node B cannot support the required security policy, then this specific PDU session is rejected. And user plane protection was mandatory to support in 5G, but we had only two code points, like 64 kilobit per second, or the maximum data rate the UI supports. The problem was that the UI would never indicate the maximum data rate because the chipsets were not able to provide this kind of user plane integrity protection. In Release 16 now, the UI has to support all data rates. What is interesting to mention, this is only a requirement to the UI. We don't have a requirement that the G-Node B has to support all UIs with user plane integrity protection. In any case, in order to prevent the attack of DNS hijacking, which was only possible because user plane integrity protection was not available. It was now recommended in Release 16, in addition, that the UI and the 3GPP DNS server should support secure DNS, which means that the DNS is over DTLS. This requires some pre-configuration of the UI with some credentials. This is about the horizontal and vertical KG-Node B derivation. There are a couple of parameters involved. One is the next hop parameter, which is an intermediate G-Node B key, and the other one is the next hop chaining count, NCC, and which is used with 0, but if you see in the figure, so only the value with 2 is used, basically. And the maximum value would be 7. The big difference is whether you use horizontal or vertical derivation is whether you have the KG node B stored in the UE and G node B or not. And this basically depends on whether the UE was just in RC inactive mode or it went to RC idle mode. So if the UE was in RC inactive mode, you use the horizontal key derivation because they have the G node B key. And if you don't have the G node B key, then you will use the KAMF key and the provisioned NH value to derive the next G node B key, basically. So now we come to the next independent procedure, which is the steering of roaming and UE parameters update. So this is performed from the home network always to the UE, and the intention is to configure the UE in the roaming network with different type of information. The steering of roaming is envisioned to be performed within the registration request procedure, while the UE parameters update can be also occur afterwards and updates parameters like the UDM instance. Because if you have the initial registration request and the UE will conceal its SUKI to a SUKI, it also has to put the UDM instance ID, because there may be different UDM instances and not all of them host the right SIDF with the right private key to deconceal the SUKI to a SUKI. And if you would go to the wrong instance, then the initial registration would fail, even the UE is legitimate to access the network. So this is the only thing, some kind of maintenance procedure, but the steering of roaming has to do that the operator wants to change the list of preferred PLMNs or access technology combinations, and then it may be that the PLM where the UE is currently trying to register is not one of the preferred ones. So the UE would basically deregister and try to register to a different PLMN afterwards, which is, of course, not in favor of the currently serving PLMN. For this reason, the message needs to be protected so that it doesn't, because the AMF can see, of course, all the content of the message, which is sent to the UE. So for this reason, the AUSF uses the stored KAUSF to compute a kind of message authentication code for integrity, and also has a counter for that. So which is counting the messages to be sent. The UDM will then use a key derivation function with the key and the message content in order to generate this MAC-I. The MAC-I is basically then truncated to 34 bits and then appended to the message. The UE can then, because it also has stored the KAUSF, verify this message and can store then on the USEM. So it can see whether the AMF, for example, changed the message in between to try to be more higher priority PLMN or something like this. And the UE may send a reply to this message if requested by the UDM. And the same principle basically applies to a UE parameters update, where the message is in a similar way protected by the KAUSF of the AUSF, and then sent to the UE in the visited network. This procedure is about the secondary authentication, which is also very new in 5G. It is about an optional EAP authentication after the primary authentication, where the UI and an external AAA server in a data network authenticate basically the access towards this data network. And this is triggered by the PDU session establishment request of the UI. And only after this authentication was successful, the UI is able to connect to this data network and to establish this PDU session. This is a very new procedure in 5G. So we have, of course, the interworking with 4G, the previous generation. And this requires some a security context mapping from 5G to 4G. And basically, it works the best if the AMF and the MME are connected via the N26 interface. So in that case, from 5G to 4G, the AMF is generating already the full security context for the MME based on the 5G security context. And then you get already the mapped KASME for the MME. You send the EKSI, the keyset identifier for EPS, the NH, the NCC pair. You have the uplink downlink NAS counts. You will give the security capabilities for 4G of the UI and the selected EPS NAS algorithm identifiers. If it's going the other way around, it's different because the MME just sends its EPS security context to the AMF, and the AMF is basically deriving a KAMF and some temporary GNodeB key from the mapped KAMF. And so this is the AMF may trigger some re-authentication after the active session is terminated. And we have also the so-called non-standalone security, which means that the GNodeB is connected to the eNodeB for a fast rollout of 5G. So this means that the eNodeB is responsible to generate the GNodeB key and give it to the GNodeB, which is acting like a secondary cell in 4G. 4G already had the concept that you can have a secondary cell for dual connectivity. And this is basically the same concept, just the GNodeB is acting as a secondary cell. For this scenario, user plane integrity protection is not available. This has the reason that the PDCP layer could be split and on both nodes, and then the security policy is very difficult to handle. But this is still studied in release 17. We have the service-based architecture security. This is the new security because we have these new service-oriented architecture of these network functions. And so a network function itself can act in two ways, like a service producer and a service consumer. And there are two ways to authenticate between network function and the network repository function. Network function always has to authenticate to the network repository function because this function will kind of proxy the requests between the network functions if some function is discovering another network function. So one possibility would be explicitly transport layer security with TLS. Another one would be implicitly that you use network domain security, that you have like certificates. And for the authorization procedure, OAuth is used with TLS, and they have the following roles for the NRF and the NFs. So the NRF is the OAuth authorization server. Then we have the NF consumer, which is the client, and we have the producer, which is the resource server. Then we come to the Internet Connect security, which is also basically using similar technologies as for SBA. And we had the problem that on the N32C association between two of these security protection proxies between two networks, you cannot make an IPsec tunnel because there are these IPX providers. They do these mediation services where they modify parts of the message and align them based on the customer requests of the next PLMN. So basically, if you have an IPsec tunnel, it's very difficult for those service providers to stay into business. So we have another interface, the N32F, where the HTTP requests are rewritten to JSON, and then the SEPs apply the end-to-end integrity and confidentiality protection, and then use web encryption and signature with symmetric keys from the TLS key exchange before, and then you can, as an IPX provider, modify, append, and sign changes with these JSON patches in the specific parts. Now we come to non-3GPP access. In release 15, we specified basically the untrusted access. The untrusted access is one of the two basically trust relationships of the operator to the non-3GPP access, which means that the operator does not trust the access point. Like you may use an access point in a coffee shop, and you can still establish an IPsec tunnel to this N3 IWF in the network of the mobile operator to use some specific services. This kind of untrusted access is very popular because the mobile operator does not need to manage the access points somewhere. So you only have to have the gateway, and the UI makes an IPsec connection to this gateway. And then you can use operator services like, for example, a popular service is voice over WLAN over IMS, which is realized in this way. Another type of access of non-3GPP is the trusted access, which means that the mobile operator manages the access points and trusts the access point. This is the so-called TNGF, the gateway function, and the trusted non-3GPP access point function. And those are then directly connected to the core network. And because they are trusted and managed by the operator. So let's look into the procedure of the untrusted access. The UI already has IP connectivity because it's connected to some access point and gets IP connectivity. And it doesn't matter how this is performed. Here, ICAuth is used to set up an IPsec connection later on, but since the request-response pairs can be only one between the UI and the network with ICAuth, we needed to have an EAP method to keep this ICAuth connection open, and this new method is called EAP5G, which is utilizing the expanded EAP type and the existing 3GPP vendor ID. So with that, the ICAuth connection will not break, and you could use both of the primary authentication methods between the UI and the AUSF to authenticate the UI. This EAP messages are encapsulated with the EAP5G protocol. So after the UI authenticated and the AMF sends the N3 IWF key to the N3 IWF, the UI can set up an IPsec connection to the N3IWF, and all the traffic is encrypted between those two entities. This is, on the other hand, the trusted access procedure, which was defined in release 16, just for completeness. We have the trusted non-3GPP access network, which is consisting of the access point and the co-located non-3GPP gateway function. So here the UE does not have IP connectivity. But the trusted non-3GPP access network is managed by the mobile network operator. So this access point can send direct messages to the core network. That means the AMF. So we do have also E5G for encapsulation here, and we have a different concept, because here the UE and the TNAP especially will generate the keys for the wireless link. So the UE and the TNAP radio connection is encrypted and integrity protected. And the UE also will set up an IPsec connection to the TNGF, which for the data traffic. But this IPsec connection is only using null encryption, because we also already have the radio encryption, and only has some integrity protection. The visibility and configurability is the last feature I want to talk about. Basically, it is possible to have very fine granularity to display what kind of security features are turned on or turned off. Like you can have the access stratum confidentiality, the access stratum integrity with different parameters, like whether it's on, off, which algorithm, what is the bearer information, and the same applies to the NAS confidentiality and integrity. The problem is that there's no procedure on how this can be applied. We only have the requirements that the APIs and the UE should be able to provide this information on a per PDU session granularity, as well as that the serving network identifier should be available for the applications in the UE. So most likely this feature probably will depend on the support of the chipset vendors. And the configurability is just limited on granting or denying the access to the user without having an authentication. Let me briefly introduce to you the Release 16 features and give a short outlook on Release 17. So those features are related to 3GPP SA3, the security group. And the Release 17 features are just started, so we don't have any we don't have any result, because we had only one meeting to talk about the features itself, or just to agree on that those features should be studied. So a lot of work was going on the security assurance and specification for 5G, which is covering several or most of the network functions in the core network, and is a collection of security requirements and test cases, basically for network vendors. We have the introduction of the mission critical services into 5G, which were there already for 4G. Then we have single radio voice call continuity, which is going from 5G to UTRAN. This handover is performed only in one direction, from 5G via the 4G to the 3G. And if the UE wants to come back, it has to re-register in 5G. So we have the security aspects of the common API framework for the 3GPP northbound APIs, and here we define some features and mechanisms for those APIs. We have the ultra-reliable, low-latency communication for 5G, and here we have basically only the security policy enforcement specified for redundant data transmissions. Then we had the feature of vertical and LAN services. Here we have defined the authentication and user plane policy handling for 5G LAN and the user plane protection for the time-sensitive communication, and we defined the so-called non-public network security, kind of private networks. We have no enhancements to the 5G location services. They are basically the same as an EPC. We have some aspects on the service-based architecture that introduce different authentication mechanisms in indirect communication scenarios of network functions. We have the new feature of authentication and key management for application based on 3GPP credentials in 5G, which is an extra level of authentication for IoT devices, and it's based on the 5G subscription credentials. It is a successor of the general bootstrapping architecture, and with the keys generated, you could also protect the user plane traffic of those devices to an application server. We have the evolution of cellular IoT security in the 5G system. So we have suspend mode enhancements for control plane and user plane. We have security for the non-IP data delivery, and also security for NAS redirection to EPC. And for the wireless and wireline convergence for 5G, we have, as discussed before, the trusted non-3GPP access, and we also have wireline access to 5G core network. Then the enhancement for network slicing was resulting in slice-specific authorization and authentication procedure. There's also the security for the new radio integrated access and backhaul, and this called IAB. This IAB node is a kind of a relay node and is relaying the signaling and traffic between the UE and the RAN. We have the security aspects of the service enabler architecture layer for verticals, which is an application layer. And here we provided some key management and security procedures. We have the security aspects for advanced V2X services in 5G. It's introduced V2X in 5G, but the only security really specified was the car-to-car communication, the V2V communication, and for groupcast and broadcast there's no real security. We do have some privacy mechanisms only. For the user plane gateway function for inter-PLMN security, this is basically only GTBU packet filtering between the two UPFs of the two PLMNs. We have then the access to restricted local operator services by unauthenticated UIs. This is a new feature where a UI without credentials can retrieve some limited services. This means like you could attach to the network, you get redirected to the captive portal like in a Wi-Fi environment, and you could provide your credit card number and name, and then pay for access for example, a day or 1 hour or something like that. And we have the feature of 3GPP profiles for cryptographic algorithms and security protocols. And these were a couple of updates to different specifications on removing weak options. For example, we have an update of the TLS 1.2 cipher suite. We have an IQ2 update. We have addition of TLS 1.3 for EAP-TLS. And there were a couple of other updates also for the network domain security specification. I will give a short outlook on the release 17 features. What we have the study on 5G security enhancements against the failed space stations. This is a study already started in release 15. We have just some passive mechanisms specified so far, but we have a lot of proposals to detect false base stations, but no conclusions yet. There's the study for the security assessment for virtualized network products, which cover security requirements and test cases for those. Then we have the user plane integrity protection study, which is also ongoing for some time, resulted in a full array support mandatory for UIs in release 16, and the recommendation of the DNS over DTLS mechanism, but it's still studying on the applicability of user plane integrity protection to 4G. Then we have the security impacts of virtualization, which is a collection of a lot of key issues and security impacts. And we have the authentication enhancements to the 5G system, which is looking into solutions of linkability attacks and SUPI guessing attacks and so on. We have the study on storage and transport of the 5G security parameters for the ARPF authentication. This results in a requirement that some operators would like to use the UDR for the storage of the long-term key. Then we have the security aspects of the unmanned aerial systems. This just started, and we have already a collection of different threats like authentication, authorization, identity, privacy, pairing authorization, security of the command and control communication, and so on. And then we do have the security aspects of the mobile edge computing. And this is looking into the authentication authorization between the UI and the Mac platform, as well as the transport security. So far, then we have the proximity services, browser get introduced into 5GS. There are a couple of key issues, mostly looking on the UI to UI and UI to network relay security. And then we have security on the enhanced support for industrial IoT, which is looking on the time-sensitive communication aspects, and for example, the security of the synchronization messages, multiple TSN domains, and UI to UI TSC. Then we have the enhancements of 5G Mpms. So this is looking on authentication, authorization for the MBS service, the protection of the traffic, and the security protection of the key distribution. And last but not least, we have some other new studies on non-public networks, where it's looking on provisioning of the credentials, credentials owned by an external identity, security of the IMS services, SNPN, potentially onboarding to an SNPN and standalone non-public network, and things like this. Then we have this security aspects of the disaggregated GNOD-B architecture. This is looking on the threats and scenarios when you separate the CUCP and you have multiple CUPs, and if they belong potentially in different security domains or owned by different parties. Then we have a very new study on user consent for 3GPP services, which is looking to identify and evaluate the requirements and solutions to support the user consent for 3GPP services, and by being compliant with the user privacy consideration. We have the security aspects for message services for a massive IoT over 5G system. This will look into the requirements and issues of the services. And we have security aspects for network automation. This is, we have the network data analytics function, and this is looking into studying the UI data collection protection of this function, the detection of cyber attacks and anomaly events, or what happens if these NWDAF instances exchange data with each other. Then last study we have at the moment is the security on AMF reallocation in case of strict slice isolation, and there are some security issues and requirements the study wants to look at if this AMF relocation will happen via the RAN. And this concludes now my presentation. And if you have any questions, feel free to contact me. Thank you very much.